Dear friends, hearty welcome to the online problem solving session organized by Maths Aspirants groups. In today's session, we have Mr. Lalit Thuwal as the resource person. He is currently a research fellow at IISc Bangalore. In today's session, he will discuss the last TIFR GS examination question paper. I'm sure that today's session will be really helpful to all those who are seriously preparing for different competitive examinations like CSIR NET, GATE, IIT JAM, TIFR exam, etc. I welcome everyone to this program. I would like to thank Mr. Lalit for accepting our invitation and joining with us. Once again, welcome everyone to this program. Welcome, Lalit.
Propose the solution, you will not be able to solve. These are not direct like other exams, GATE, straightforward problems, or CSIR NET. In all the CSIR NET, there are very good problems, but still there are some problems which can directly think and are formula based. But in the TFR exam, this does not happen, right? So I will teach you today, and I will, I have two options that either I discuss all of the problems and not writing the solutions and not telling you that how you get an idea to get the solution. Right, in this way I will be able to cover all the solution, but I think that the more important is that I discuss few of the problems, and all of you understand that how do you know that you have to solve this problem like this, and the remaining problems you can see, okay, in future, that if you want to see the solutions of the remaining problems. And let me tell you the platform where you can watch. There is channel in mathematics in YouTube. Okay, so in few days, all the TFR 2026 problems with detail will be provided there, so you can watch there. Okay, and I have also written a TFR PYQ book. Okay, so you can search in Google that TIFR solutions by Lalit. Okay, so you will get that. Okay, so there I have written all the solutions from 2010 to 2025 with, I mean, in detail, proofs and disproofs and solutions of MCQ. Okay, so let's get started now to solve the problems. So let me first take this one. Okay, so I will randomly select today. So this one, because I have assigned you before the starting of the session. So, and I will, at the end of this session, I will share also the videos. And I said that please uh, be with me till the end. So, because at the end, I will share something about NBHM and GATE exam also. Okay. So, see.
स्क्रीन चला गया.
Yeah. I realized that. So now you can see it, right? So see, what is given that if FR2R is a continuously differentiable function and S is a bounded subset, then there exists a constant CS greater than 0. The CS means this subscript is a reminder that this CS depends on S. If you choose different subsets, you will get different constants. Okay, so that's why we write S in the subscript. Okay, this is the region such that mod of fx minus fy is less than CS mod into mod x minus y for all xy in the S. So see, first of all, that what I have given, whenever you solve some problem, that use first thing that what has been given and what is our requirement. That will tell you that how you have to approach the problem, and you will get the solution easily. TFR problems are not very difficult to solve if you know the enough stuff. Okay, so see, I mean, if you have the, if your concepts are clear, so see, we have given that this is a continuously differentiable function, so we have to use the differentiability and continuity of the derivative. Okay, and we want this, see, this constant to be, I mean, this fraction to be bounded for all xy in a bounded subset. Fix a S, okay? So from where do we get this? This kind of thing we can get from the mean value theorem, right? So this thing tells us that we can use mean value theorem and the function is differentiable. Okay, so let's try to do that. Okay, then the further step will be clear that what we have to do. So by mean value theorem, okay, for x not equal to y in S, I'm writing x not equal to y because I will divide by mod of x minus y. But for x equal to y, the inequality is very clear, right? So in that case, it's trivial. We don't have to do anything because both sides are 0. Okay. So for x not equal to y in S, we have by mean value theorem, by the mean value theorem, we have mod of fx minus fy over mod x minus y is less than is equal to f dash of, let me write it, alpha x. This alpha x is depends on x and y. Okay, so let me write it xy. Okay, okay, I mean we can write it so I mean it's better to write xy, right, like this. Okay, so we can skip the comma. This xy is between x and y, right? Y is the subscript because that it depends on x and y. If you change x and y, then this might change. Okay, this number. So see, now this thing is in S. S is a bounded subset, right? So is this bounded for all alpha x? I mean, f dash is bounded on S. Yes, answer is yes, because f dash is continuous, and a continuous function from R to R maps bounded sets to bounded sets, right? So note that S is a bounded, and sorry, this is not in S. Alpha x might not be in S, but this must be between x and y, okay, in the real number line number, because S is just a bounded set. If you pick x and y, S might not be an interval, so the any point between them might not be there. Okay, so I will okay, so see, uh, note that S is a bounded subset, so there exists m greater than 0 such that S contained in, why I'm writing this, I'll tell you. Okay, and f dash is continuous since f dash is continuous, so f dash, the image of this set is bounded, right? Because a continuous map maps compact subsets to compact subsets, right? You know that. So there is a CS such that f dash of Z, I think you will not confuse if I use the X. Okay, so less than and equal to CS for all x comma y in this interval. Okay, so in S, right, for all x y in S. Is it clear? You can react. Okay, so therefore mod of fx minus fy over x minus y is bounded. So mod of x minus y is less than equal to CS for all x comma y, for all x comma y. I think I should write like this side. Okay, for all means x equal to y also. Okay, for x not equal to, I have proved that. So x comma y in S, right? Because this thing is less than equal to CS. Okay, I think, is it clear? So you got, now you learned, right, that how do you know that we should approach in this way? This is not something like that. Okay, yahan se aa gaya apne aap, right? So you can do that also. Now, okay, so any question in this? And why this, I choose this interval? Because this alpha xy may not be in S. Okay, that's why I choose. Now this is connected. So anything between two numbers will be there. So that's why I took that compact interval. So that was the reason I said that I will tell you. So okay, so now one problem from algebra. Okay, so I want to say something about this. Okay, I'm not gonna prove that, but see, this thing is asked in TIFR 2026, right? And the same thing has been asked in your CSR net exam of this year. I mean, the recent CSR net exam. Okay, kind of this. Okay, and that uses the same thing, uses the same concept that is called Burnside lemma. If you have studied the group action theory, then you might have learned about that. If you haven't, then you should. Okay, so where you can find some questions related to the Burnside lemma, because in the TFR exam, many of the questions had been asked in the previous years, which uses the Burnside lemma, and those are very beautiful questions. Okay, what I told you in my book, TFR Solutions by Lalit, ebook, you can search it in Google. You will find the use of that. Okay, so I will also present that after some time. I will show you some of the pages of that book in which I have used the Burnside lemma. Okay, this is direct application of the Burnside lemma. Let me tell you what does that say. Burnside lemma says that if G act on a set X, and so fix G denotes, I mean, those element which are fixed by G. Okay, I mean, G, if fixed G is the collection of those X in X for which G dot X is X. Okay, this is the fixed G. So this says that this sum, Burnside lemma says that this sum is the number of orbits. Okay, cardinality of the orbits. Number of orbits of the action. Okay, so this is Burnside lemma, and this is very useful lemma. And you know, the problems which were asked in the previous years in TFR were, I mean, was very beautiful and are very beautiful. While I was writing the solutions of those, then I felt that, wow, what a problem. Okay, so there is a problem in chess, I mean, which talks about the rotations of chess and equivalence classes, colorings, and all. You can look that. I mean, this is asked in TFR 2021 or 2020. Then I had written the solution of that, and I really found it very beautiful problem. Okay, so now let's discuss the solution of this. So see, S10 act on this set, right? Acts on 1, 2, dot, 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 10 acts on this, and the action of S10 is transitive, right? Because if you pick any two integers, say 2 or 5, then there is a permutation which sends 2 to 5. Okay, it means that the action is transitive. If the action is transitive, then it means the number of orbits. Please raise your hand if you know. The action is transitive, then the number of orbits. I want to see that how many of you know how many will be there. Okay, so Sri Sendhu, you tell how many orbits will be there.
So one.
Yeah, there will be only one orbit, right? Because the action is transitive. Because if you pick any two elements here, then you have a permutation which sends one to another. So it means there is only one orbit. So this by Bernoulli lemma, this is cardinality of G 10 factorial summation, sorry, sigma in S10, cardinality of fixed alpha, sorry, sigma is equal to 1 number of orbits, because there is only one orbit and this is equal to 1. This is a true statement. Okay. So to learn more problems and more about Bernoulli lemma, you can look at the books, and to learn the problems of TFR, please check out my book, okay, on the TFR. Sorry, sir. So now, so I have I hope you are enjoying. So there is a question of so let me discuss this one. Okay, this is also the beautiful problem. All the problems are good, but this one uses the pigeonhole principle. So first off, to solve this problem, you should know some facts. Okay, so two permutations. First of all, that in Sn, any permutation can be written as a disjoint product of disjoint cycles, right? So this you should know to solve this problem. And how to find the order of elements of Sn, you should know that, right? And two permutations in Sn are conjugate if and only if they are of same cycle type. Cycle type means, I hope you understand, right? Okay. Okay. So see. So what is given that sigma 1 dot 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 sigma t be the elements of the permutation group S236 such that sigma I cube is the identity permutation for each I, then there exists I and j between 8t and 1 such that sigma I is conjugate to sigma j. So see, first of all, what has been given? What I told you, that first you should know what has been given and what you have to, what is your requirement, what you have to get. Okay, it is given that sigma I cube is equal to identity for all I in given for all I in S2, sorry, I belongs to 1 to 80, right? So what does this imply? So what information it can give? This gives that sigma I, order of sigma I is, you tell. Order of sigma is, anyone?
Either 1 or 3.
1 or 3.
It divides 3, right? So it can
Oh,
be
it-
either 1 or it divides 3. So it can be either 3 or 1. Yes. So if the order is 1, then it is identity permutation. Otherwise, it is of the some cycle type C. Those permutations in S236 can have order 3. Which permutation can have order 3? Whose cycle? I mean, let me tell you, kind of this. Only which are product of 3 cycles or a 3 cycle. We can say that which are product of 3 cycle, right? None other than that. So how many are there cycle types which are product of 3 cycles? We have to count that. Okay, so let us count. So see, so for that, it will correspond to the partitions of 236, which has only 3 and 1 as terms, right? So try to convince yourself first. You understand, right? So it means it will be something like 3k times plus 1. How many times? You tell. How many times? Okay, I think I should say k times. Okay, I mean k times and L times. That we don't need that how many times exactly. So any partition which is like this correspond to a cycle type and vice versa, right? Okay. So now you think that in the maximum three can appear, the maximum number of three can appear in a partition, in such partition is 78, right? You confirm it, please. 78 into 3 is 234, right? Then two ones. So we cannot have more threes than 78. So we can also have 77 threes, right? Like this, and other ones. We, in this way, at the end, we can have no threes, all ones. Okay. So what does it mean? It means that, so how does this partition correspond to a permutation? This means the permutations of this kind: 3 cycle, dot, 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 a 3 cycle. So 3 cycles are 78 times, and yes, and two elements are fixed. Okay. So these all are how many permutations? How many cycle types? 79, right? So these 80 will be among these 79. Right. So by pigeonhole principle, there will be two which are same, which are of same cycle type. I mean, not same, which are of same cycle type. Okay. So they must be conjugate. Okay. So we can say, I'm not writing it now. There are I and j such that sigma is conjugate to sigma j. Okay. So this is true. So now you can feel the beauty of the problems, right? Okay. Okay, so let me take the another one. Okay, so one problem, this one. So this one is easy. Can you try yourself first? So think about it. Then I will tell you the solution, and then mark the point which you missed. Okay. Okay, so think like that when I will be telling you the solution, then think, oh, this is the point what we did not get while we were solving. So we should think like that. Okay, so try to solve it. I give you 1 minute. Time it starts now. And raise your hand, okay, if you have solved it. See, let me give you a hint that if some polynomial divides another polynomial in an algebraically closed field, okay, then every root of the factor, I mean the say ax divides bx, then every root of x will be the root of bx, right? And vice versa. I mean, if every root, and conversely, I mean, if every root of x is a root of bx, then ax must divide bx. No, I should not say that. I'm actually that depends on multiplicity of roots also. So I mean, you can use this kind of thing, okay? That is not actually true. That if every root of some polynomial is the root of another polynomial, then the first polynomial should divide the another one. That's not true, because that depends on the multiplicity of roots. Multiplicity should be less than n equal. Okay. Okay, let me put another one also. Okay, till then you can think about it. So let me choose the another one which we are going to solve. Now let's take some problems from part A. This one. And this one. So yeah, if you can't solve the first one, then think about the second. And for the second one, the hint is that, see, suppose that you want to counter the first one. You should pick a non-diagonalizable operator whose, just first try to pick a operator whose null space is 0. That will make it easy. Okay. And you will be able to easily counter it. Try to do that. I mean, you should do that. Okay. So I hope you are doing. Okay. So let me discuss the first one. Solution. So see, this says that px minus x divides the polynomial ppx minus x. So if this polynomial will divide this one, then each root of alpha will be a root of this polynomial with the same multiplicity. Okay, multiplicity also you should take care of. I mean, so you should not ignore that. So suppose that alpha is a root with multiplicity m of this polynomial px minus x, right? So that means then p alpha equal to alpha. Then is alpha is also a root of this? So because we are checking that this is true or not, see, p of p alpha minus alpha. Since p alpha is equal to alpha, this means this is p alpha minus alpha, but p alpha is equal to alpha, this is 0. It means each root of this polynomial is a root of this. But if the multiplicity is, because it happens, see, x minus alpha square cannot divide x minus alpha, right? Because the multiplicity is greater. So we have to verify also that the multiplicities are same. Suppose that it has multiplicity 2, for example. You will do the other, I mean, calculations. I will leave it for you. So that it has multiplicity 2, then the derivative will also vanish, right? Its derivative is p dash x minus 1. So it means p dash alpha is equal to 1 in that case. Then does the derivative of this also vanish? Okay. So see, if you take the derivative, this comes out to be this, right? You know the chain rule, right? Chain. Okay. So put alpha, P alpha, P dash alpha. Okay. P dash alpha minus 1. But P dash alpha is 1, right? In that case. So P alpha is alpha. This comes out to be P dash alpha minus 1, which is 0. Okay. In this way, please verify that if the multiplicity is M, then mth derivative, I mean, m minus 1, mth derivative will non-vanish, but m minus 1th derivative will vanish, and verify for it also. Okay. Then this statement is true. So you will do that because I have told you that how you have to do it. Okay. Fine. So now this one. No, before, yeah, let's do this one. Okay. So I will not ask you to solve this and let me know the answer because answer is visible. So I ask you to just solve it and understand that why first one is correct. Okay. See what you have given, that I have already given you time to think about it. So consider the set. This set is the set of all. Can you recognize it? Set of all something.
Nilpotent matrix.
Right. This is set of all matrix. This set of all nilpotent. See, you may think that yes, this is contained in set of all nilpotent matrices, right? At the first glance, but the reverse inclusion is also true. Why? Because any nilpotent matrix of order 10 must vanish. I mean, when you raise the power 10. Okay, this is because all the eigenvalues are 0. So characteristic polynomial must be x to the power 10. Right? So x to the power 10, by Cayley-Hamilton theorem, it will satisfy that. So a to the power 10 must be 0. So it is exactly set of all nilpotent matrices. So see, and for each a m, yeah. So define the linear transformation. We define the linear transformation. We will act on vectors by a. Okay. Then which of the following is true? For all a in A, we have determinant TA is 0 and trace TA is 0 C. This TA is a nilpotent operator. Why? Because TA to the power n, 10 x, when you act 10 times successively, you get this, right? But a to the power 10 is 0. So it means TA 10 act by 0. So it means this is identically 0 and TA for is a nilpotent operator, right? Written for all a in this A. Okay. So now what are the eigenvalues of a nilpotent operator? So that we can find 0, right? Only 0 are the eigenvalue, right? So see, let me tell you why. Because see, some nilpotent operator TA, let's write T, has eigenvector V and eigenvalue lambda. So, but for T to the power K, I mean, it has some index. So applying that many times. So T to the power K, V is equal to lambda to the power K, V. Okay, right? But T to the power K will vanish. So V equal to, this comes out to be 0. But this is a non-zero vector. Okay, so it will have some non-zero entry. So, oh, sorry, I mean in some vector space, right? Yeah. So this is true for some any vector space. So you know that this must imply that what you must have proved this kind of properties in vector spaces, right? If A into some non-zero vector alpha is 0, then A must be 0. Right? Because this is not 0, because V is not 0. Okay, so it means lambda to the power k is 0, and lambda to the power k is 0 in a field implies that lambda must be 0. This is true for any field, any vectors. This, okay, not only for this antenna. It means it has only 0 as an eigenvalue. So their product is the determinant, which is 0, and their sum is the trace, which is 0. So no need to think about others. Okay, these are just, I mean, not equal in some one of the two. Okay, so, and this one. Now, how do you think about this one? Let T Rn to Rn be a linear map such that T is not equal to 0 and Rn can be written as a direct sum of range T and null space of T. Consider the following statements. First, T is diagonalizable, and second, there does not exist any integer k such that T to the power k equal to 0. Which of the following must be true? Okay, which one? It says that first one is false. So we have to determine which one is false among these statements and which one is true. Or, I mean, yeah. So see. I mean, we have to determine are these false or true. Okay, so T is diagonalizable. So does that imply? But see, if T is diagonalizable, this is true. That you can write Rn as a direct sum of a range T and null space T. On the other hand, if this happens, is T diagonalizable? No. How do you think about this? First, let me take some operator which has no zero eigenvalues, so that which have all non-zero eigenvalues, so that null space is 0 and it is automatically direct sum, right? Range n which is onto operator. So this is automatically direct sum. So I mean, it is enough to take that null space is 0. Okay. So, and some non-diagonalizable operator. So let me take this one. 1, 1, dot, dot, dot. I mean, all this is Jordan block of order n. So if you define the linear transformation by this act by A, then this satisfies that you can write Rn as a direct sum of range T plus null space T, because null space is 0, right? This is null space. Why 0? Because this is invertible matrix. Okay, because X equal to 0 implies that X must be 0. So that conditions automatically hold. But is this diagonalizable? Raise your hand if you think no, this is not diagonalizable and you know the region. Raise your hand. And if you don't know, I want you to think for a let me stop for a moment and I want you to think. And you should think that why this matrix is not diagonalizable. Okay, you have 1 minute. Please think about that. All students, not only few. Okay, think about that. You can think. Okay, just realize that this is not a diagonalizable matrix. You have many ways to think that. Okay, you don't have to answer now. I will name the student that will answer. Okay. Okay. So let me ask someone. Abhilip Shah. Why is it is not diagonalizable?
Sir, geometric multiplicity of 1 not equal to algebraic multiplicity of.
Okay, fine. So algebraic multiplicity and geometric multiplicities differ. And see, another way is to see it that what is its minimal polynomial? That is not obviously x minus 1, right? Minimal polynomial of MAX is not obviously x minus 1. And we don't care that what it is. It is, let me tell you, it is exactly x minus 1 to the power n, because this is a Jordan block, and for that, minimal and characteristic polynomials coincide. So, and it means the minimal polynomial has multiple roots. Okay, that means A cannot be diagonalizable, hence T is not diagonalizable. Okay, because the minimal polynomial of T and A is same. So it means that the first statements need not be true, while the second one is true. Why? There does not exist any integer k such that t to the power k equal to 0. It means that t is not nilpotent. Okay. So think about it. Why t is not nilpotent? So there are other ways. There are many ways to think it. So either you show that t to the power k is never 0 for any k, or that you show that there is some eigenvalue which is not 0. Right? And you have given that t is not exactly 0. Okay. Remember this. You might forget it. Raise your hand. Okay, Sri Sendhu, you tell.
Sir, then image T will be contained in kernel T, right? So, I mean, we can't write the direct sum then.
If t to the power k is 0 for some k, then why image t will be contained in kernel t?
Sir, because like T of like T to the power K minus 1, that is image T. So then kernel T will contain image T. And that is not possible by our hypothesis given in the question.
How? You say that t to the power k v equal to 0, say for all v, then what do you mean? Okay, very nice. So this means t v equal to 0 for all v in Rn. Okay, so that means that t, it is contained in the kernel of t to the power k minus 1.
No, sir. T composed T K minus 1V.
T composed. Okay. Okay. So you want to write like this. T com okay. V equal to 0. So
Sir, then image T, this is, T to the power K minus 1V is contained in image T, right?
yeah.
This is, so yeah, then image T will be contained in kernel T.
But that does not apply it. I mean, if some smaller part is in somewhere, but the bigger part might not be. And this might be 0 even. What does it with 0? What if it is 0?
Oh, okay, sir. Okay.
That will, and 0 is common to both of them. So see, I want you to think about it that you have given that t is not 0. So there must be some non-zero vector in the image. Right.
Okay, sir. Yes.
So why don't you think about that? So I want student you answer this one, okay, not me. So let me give you a hint that how do you proceed, and in this way you may think also this is not the, but you have to rectify that. So see, V is some vector in range T which is not zero. This is in range T, okay? So it must not be in null space of T because it is direct sum and it is non-zero vector. So not equal to zero. So this is not a good way of writing like this, but okay, let's say that V is a non-zero vector, which is here. So then there is a X which maps to this. So can you, so that T to the power K act by not by zero on some vector, does not act by zero on some vector. Some vector can you find? Okay, so let me leave it as a homework. Okay, you can think about it. So see, now let me tell you that how do you proceed. So you have this now act by T. Okay, then you will have T square. Here you will have T, TV. So is TV zero? Realize that. Can it be? Because this is in the range. So I'm just letting you know the solution actually. This is in the range, but not here. So it must not be zero. Okay, think like that. Okay, so at the end you will get that there is something on which some TK does not act by zero, on which a TK given TK does not act by zero. Okay, so and I will give
So
take another
cyclic
session,
vector.
then I will ask you. Okay,
So
yes,
cyclic
yes.
vector. So I mean,
No, I'm not saying cyclic vector. I'm just telling you that you may proceed like this. Okay. Okay, so I have less time. Now I want to discuss one or two questions. But before that, let me show you something, what I was talking about. Okay, so the TIFR solutions book in which I have, I said that there are problems which uses one-side lemma. So for that, I need to present my screen. Okay, so you will give me 2 minutes. Okay, in 2 minutes, I'll show you. See, so can you see? Let me know, please. So is it visible? I can't see the reactions. Okay. So see, this is TFR book in which, this is content.
Sir, when will be this book available?
No, it's available actually. You can, I mean, if you are interested, you can purchase it. So let me show you what the content is and how the solution has been written so that you can check it out. So TFR 2010 to TFR 2015. Okay. So see, but I just want to show you. Okay. So if we see TFR 2025 solution. Okay, in this way the solutions are written. This is the part A, multiple choice questions. Question 1. So the detailed solutions are there, not only just solutions. Okay. For each of the questions, the detailed solutions you can see, for example, and I have drawn the diagram. So whenever it is necessary, see like this. Okay. And in the second part, when true false questions are there, so see, I have written the solutions in very detail. If the statement is false, then I have written here, disproves, and these are in very detail. Okay, each and every step is written. So see, proof of the true statement, proof, disproof in this style. You can see it's like a book. I mean, a mathematical book of the course. I have proved everything as you see in the reanalysis books or any book. So see, this is the proof of, any isometry x to x from a compact matrix space to itself is surjective. See, so long proof. I have included alternative proofs also. See, So in this way, and there are diagrams wherever it is, possible. I have included the diagram to understand the solution of the problems, and all the see this one. Like this is from this problem is from TIFR 2024. This talks about the homeomorphicity of two sets, which is a composed union of parabolas, say, and hyperbola. So I have drawn, at many instances, I have done that. Okay. So all the solutions are there. Okay. See, I have discussed many things which really might be helpful in another exams also. Why? Because see, let f(R2R) be a differentiable function that is a solution of ordinary equation. This is the question of 2024, right? So in this C, I can directly solve this problem, but I did not solve it directly. What I said, first the equation, next by existence in, okay. So what I say here, once the given ODE has a unique solution, one can solve it directly to find the solution and check whether it is bounded or however. I will approach it differently to demonstrate a method that helps solve similar problems where directly finding the solutions is not easy. And you must have seen this time a question which involves this kind of method has been asked. And this kind of questions has been asked in many of the exams, many times, CSIR, NBHM and all. Okay. So I cannot let you know all the things what I have done in this book, so you can check it out. Okay. So, and I was talking about one-side lemma, right? But I must show you that where there's a problem which uses one-side lemma. I think it is in 2020 maybe, or 2021. Okay, 2021, I think. Yeah, part A, 10th question, right? Yeah, I think, if I remember correctly. No. Oh yeah, I remember correctly. So see, consider the 8x8 chessboard. So this by Bernstein lemma, and this is asked this time, right? And this is also asked in CSIR net. So see, this is very nice problem. What I said, this is the problem of chess, and you might not feel at the first glance that this is not the problem of group theory, but this is okay. So yeah. So let me come back and we solve the problems. See, now let us take few more problems from part A. Okay. This one is very nice one. Okay. So I like it actually. So you will also like it. So let's solve this. So first, for 2 minutes, you think about it. That what is the first thought comes in your mind, and you think that we should solve like this. Okay. So you already know the correct answer. So try to solve this. And that book is available, okay, in a mathematics website. You can search it on Google. What you have to search, TIFR solutions by Lalit, ebook, then you will find it. Otherwise, at the end of paper, there will be a link maybe in this paper. So see.
Can you organize this book as chapter wise also?
We will, what is the question? Is it chapter wise, year wise? It's
Chapter
year
wise
wise.
or topic wise?
Year wise. TIFR 2010, 2018, as in the exam, same order. Okay. So see, I will answer your questions at the end of this session. Okay. So let's solve this problem first. Let G1 infinity to R be a function such that G1 equal to 1 and G dash X equal to 1 over X square plus G square X for all X greater than equal to 1. Okay. So then which of the following statements is true? See what is given. How can you find? First off, our first task is to see that whether limit gx exists or not. How can we see that? We have given this information g dash x. If g dash x is given to us, what can we get from it? And this is clearly greater than equal to 0. It means that g is a monotonically increasing function, right? First thing we get that g is monotonically increasing. Okay, let me write everything very clearly for this problem. G is since g dash x equal to x square g square, x square plus g square x. So this is greater than equal to 0. In fact, this is strictly greater than 0 for all x greater than equal to 1. Okay, which implies that g is monotonically increasing. Monotone, g is monotone is enough. Okay, so now g is monotone, and it means that either g is unbounded, or if it is bounded, then limit must exist, right? Yes or no? But how do we know about that the g is bounded or not? Because monotone functions, if they are bounded, their limit exists at any point. Okay, if they are unbounded, then their limit tends to either in minus infinity and infinity. It depends on that. It is monotonically increasing or decreasing and where it goes. So see, but we can find the bounds of g from here. See, it says that g dash x again from given condition we have g dash x, and I will find a more finer bound than 2. Okay, here. So how can we find that? See, x square, g is monotonically increasing, right? So the least value of g is, can you tell me? That is given. The least value of g is
1.
1, right? Because at 1 it will take its least value. Okay, the 1 is the infimum. So 1 is the infimum. So it means that this thing is so g will keep on increasing right now. So right, this means this x square plus 1, because gx is greater than equal to 1 always, right? So this value will bigger, and if it is bigger, then it will be lesser. So see, now we have this g dash x is this. Now we can integrate it. So let me write it t. Okay, t square plus 1. Now what do we want? We want, okay, we have given 1. Okay, so integrate it from 1 to x. Okay, for any x. Inequality is preserved, right? We have for any x greater than equal to 1. We have this, right? Integrating, we get that gx minus g1, and the another side is 1 tan inverse x minus tan inverse 1. Tan inverse 1 is
pi by 4.
okay, so minus pi by 4, right? Okay, so now it means gx is tan inverse 1 x minus pi by 4 plus 1. Okay, so this means that gx is bounded. Okay, so limit extending to infinity gx, the another side comes out to be pi by 2 plus 1. So this means this is 1 plus pi by 4. It means the limit gx exists and must, this exists because of the monotonicity. Okay, so must be less than equal to 1 plus pi by 4. I think this is strictly less than 2, right? more finer bound we have got. Is it okay? So what is the correct option? It means this. So I think you also feel that this is one of the nice problem. So, okay, you understand the solution? So is there something we cannot think in the exam? I mean, I told you that how you should think it, right? Because first of all, we have given the g dash x, okay? We want to know that the limit extending to infinity gx exists or not. How do we know that? And what information we have given? The information we have given only about derivative. From the derivative, we have to extract the information about the gx. So first information comes to our mind that this quantity is strictly greater than 0. It means gx is monotone. Now, your mind must say that, okay, it means limit exists either infinitely or finitely. When finitely? When it is bounded. But how can I find the bound? Okay, so I can integrate g dash x. So, but how can I integrate? Because I don't know g square x. Okay, but this is must less than equal to 1 plus x square. Like that, should I integrate 1 by x square? Yes, you can integrate, but you will get not, I mean, some bound which may be 2. I think in this case, you will get the bound 2, okay? So, but we have used something more that because the infimum least value of j is 1, so we are finding more finer bound. So we are getting the more finer bound for the limit. More fine, I think I should say we are getting the finer bound, not more finer. So, okay, in this way, we have solved the problem. So it's not difficult at all, okay? If you know the necessary concept, if you know that what is given to you, and remember, in every problem, more or less, the argument are same, but they have been used with, they are used with variations, different variation, okay? I mean, the concept which are used are same, but with the variations. So you have to learn that. Okay, then TFR problems will be difficult for you to tackle in the exam itself. Okay. So now we have time and we can consider to solve few more problems. Okay, this one is very one of the nice problem of analysis also. So when I was being interviewed, so it was asked to me also in IISc. So I have solved this problem at that time. So that's why I really like it. So let's solve it. Okay. So what does this say? That for any differentiable function gr to r, let ag equal to x in closed interval 0, 1, gx equal to 0. This is the set of zeros of g in the closed interval 0, 1, and this is the set of zeros of its a derivative in the closed interval 0, 1. Okay, ag and bg. And s is the set of those functions for which the set of zeros in the interval closed interval 0, 1 of g and its derivative does not intersect. Okay, so those functions. So what does it say? That for all g, the bg must be finite. For all g, the set ag must be finite. There exists a g. So let me tell you the correct answer. Okay, you can eliminate others by taking the examples. You will do that. It's your work. So let me do what is correct. Okay, solution C. Okay, how many of you can solve it? By the way, I should ask you first. Raise your hand if you can solve it. You have to raise your hand, not read. two of you. It's not difficult to solve, okay? So how do you think about it? Let me tell you. So you have to use the compactness of 0, 1 and Rolle's theorem. Okay, let me tell you how you can do it. So see, for all G, the set AG must be finite. So suppose AG is infinite. What happens if AG is infinite? Think like that. In that case, you have a sequence of zeros like this. If AG is infinite, then you have a sequence of zeros. So this, you have an infinite sequence, okay, of distinct points in AG. So because all the zeros in AG, right? All the zeros are in AG. Okay, so we will have a converging subsequence of this, right? The converging subsequence of this because of the compactness of 0, 1. Or you can say Bolzano-Weierstrass theorem. Okay, so we will have a converging subsequence. Say that again denoted by x1, x2. Okay, we can pass to a subsequence and denote it again by x1, xn. It converts to L, and it is monotonic. So this is closed interval 0, 1. So let me take like this. Suppose the sequence is like this, and you can consider a monotonic sequence. Yes or no? Monotonic decreasing or increasing? Let me tell you. I will tell you why. So can you tell me why you can consider a monotonic? You can pass to a monotonic sequence. Why? Because what information you get that you only have a sequence. It does not mean that it's monotonic. You have a sequence of zeros of G in the closed interval 0, 1, which converts. That comes from the compactness of 0, 1. But why that must be monotonic? Not that might be monotonic, but we can have a monotonic subsequence of zeros which converts to a point L. Say that it's a monotonic decreasing. Okay. So can anyone of you tell me why? Okay, Aman, you tell.
Because every real sequence has a monotone subsequence.
Right, but yeah, every sequence has a monotonic subsequence, right? Okay, and we will pass to that subsequence and again denoting the subsequence by xn. Okay, so our goal is to get a monotonic subsequence converging to L. So it will easy to apply the Rolle's theorem. Okay, so in between xn and x2, applying Rolle's theorem over and over again, you will get a sequence y1 and y2 because of the sandwich lemma. This must converge to L also. And see, because G vanishes on each of the xn and converts to L, because this is a zero sequence, by the continuity of G, G of L must be 0, right? Because this is zero sequence and it converts to L. Xn converts to L, sorry. Xn converts to L. So Gxn must converge to GL, right? Because of the continuity of G. But Gxn is always 0. So this is a 0 sequence. So GL must be 0. It means GL is 0. Now, y1, y2, all these are zeros of G dash. By Rolle's theorem, you can get. Okay. So G dash yn is 0. And you may ask me that we can also have a monotonic increasing sequence. In that case, the proof is similar. Okay. So G dash yn is 0 for each yn. But your derivative is going to be continuous? No. Okay, so we don't need it continuous. Okay, let me find the G dash L. Okay, G dash L is limit x tending to L, Gx, GL. If it were given continuous, then by continuity we can immediately implies that G dash L is 0. Otherwise, right, this limit Gx over, what do we get? X minus L, right? Because GL is 0. X tending to L. Now what we can go along the sequence limit, n tending to infinity, because we know that this limit exists. So we can approach along any sequence and get the limit, right? So we put xn. Okay, so I don't need actually this one, Rolle's argument, okay? This were needed if G is given to be continuously differentiable. This was helpful, otherwise not. Otherwise, you can use this one, okay, what I'm letting you know. So at this point, I realized that G is not given to be continuously differentiable, so I change it. So we don't need to apply Rolle's theorem. So this comes out to be xn minus L. See, the xn are different from L, okay? So this is well defined for each n, and gxn is 0 every time for each n. So this is 0. It means g dash L is also 0, okay? If G is continuously differentiable, then you can also use the Rolle's theorem to conclude that G dash L is 0. Otherwise, we don't need. Otherwise, we can directly do it, okay, by the definition of differentiability. It means that G dash is also 0. In that case, L is a common 0 of G and G dash, okay? So there is something which is common in AG and PG. So G is not in S. It means we get a contradiction. So for all G, must AG be finite? Is it clear? This thing is extra, okay? This one, the rule is, that is helpful only in case G S is continuous. Okay, so, but what I was telling you that I had been asked this question. I had been asked both the things. First, it is continuous, continuously differentiable, and once it is not continuous. No, I did it, but they have given it to me. But they want me to use Rolle's theorem. Then I mean, they said that, okay, what F double dash? Okay, F double dash G double dash will also be 0. So then I cannot use this thing actually. But if G double dash is continuously different, G is twice continuously differentiable, then G dash L also be 0. Because of this argument, you can use that, okay? And think about it at home. So I think we have to stop. It's a good time to stop. Not good time, but we don't have enough time. It's already 9:30. But at the end, you can share your feedbacks. Okay. About the today's session. If you want to share your feedback, please raise your hand. Okay. Okay, Vaibhav. Okay, I'll come to you. So first raise your hand whoever want to share their feedback. Okay. Okay, so first let me come to Archana. Archana. Yeah, you can say it. If possible, you can turn on your video, okay? And otherwise, it's
Yes, sir.
okay. So
Okay. Good evening, sir. Sir, I am Archana. I have completed my BSc, and this is a drop you have taken for JAM. So I attempted the TIFR, but not in a great way because compared to JAM, it's tougher. So I attended very few questions, and this session really helped me in knowing a lot of things that I lacked. It kind of bridged the gap between what I knew and what I didn't know. So it'll be really helpful for me for NBHM as well as for JAM in terms of strategies and all you told, like how to think for a particular question and all. So I really enjoyed the session, and as always, your session was really good, really in-depth analysis and everything was there. So thank you for the session and hoping for more from your side for, especially for JAM. So
yeah, thank you
thank
so
you.
much. I will
Thank you.
definitely,
Yes, sir.
conduct sessions for JAM also, try to conduct. Okay, so, and
Sure, sir.
NBHM also. Okay, thank you so much.
Sure, sir. Thank you, Vinod, sir, for organizing through Max Aspirants. So thank you, sir.
So, seeing Dharmendra. Yes.
Yes, sir. I am Dharmendra Singh from Kashmir, UP. Last year, I resigned from my job for TIFR and other exam also. But this year, I did not fill this form because of some problems. And I feel some little bit tough these exams like TIFR and CMI also as compared to JAM and programs also. I cleared TFR exam in about IISc days 2009, as I remember, and about not clear, but I did not pass interview, which was held at TFR camp. So I felt very good, but because of interview failing, so I motivated, but because of some problem in my father's death, I joined the BARC in library department, and there I attended so many lectures and conference and PhD viva also, and I felt very good, and I felt about physics, mathematical physics, and other also because mathematics department is not directly, but physics people are doing good math and number theory also, and one more topic also on their own without guidance any. And many scientists I meet too who did not PhD, but they did self-research and got DSc also. So
Okay.
can you please tell about these exam TFR and CMI? Because I these are very little tough. So how to prepare for these with TFR and with IITM? Can you tell?
Okay. So you have a
about
question.
your book? We organize this book as chapter wise or topic wise, so that when
Okay.
we
Okay.
are
Thanks. Thanks for the suggestions. Okay. So yeah, Aman. Yes, Aman. Do you want to say something?
Yes, yes.
Yes.
Yeah, the solution, this session was very useful. Particularly, I learned a lot in the last question, and because that question showed me the how to connect the different theorems, even small theorems like role theorem and sequence theorems on sequence, and use them on this kind of problem. Usually when he sit in exam, we could not think many of ways this is this way, because of either of exam pressure or because we did not do this kind of problem at all. That is a very useful. I am very happy that last problem pleased me the way you solved it. I learned a lot at it.
Okay.
It will
Okay.
help me. Yes.
Okay. Thank you so much. Okay. Okay. So I really also enjoy to tell you the solutions of all these problems. So we will solve, I mean, more problems of TFR in upcoming sessions. I would happy if you would join. Okay. So let's end the